Welcome, Dr. Hammond, and congratulations for your 2015 Michael Fry Award.
Thank you very much.
And I heard that you're giving a talk this evening, and would you like to tell us a little bit just before the talk so that we are also excited as much as you are to tell us about your research?
Okay. Well, I'm very honored to be receiving this talk, and so I'm looking forward to it. So I'm going to, whereas normally when I give a talk, then I would focus on one recent piece of work and probably go into that in quite some detail. Today I'm going to sort of take a meander down the whole pathway that we work on and then get a little bit more focused at the end. So it's really going to cover a lot of years' work.
Oh, that's very good. Some of the new investigators will get benefited from that because they will be seeing the entire path and the work that's gone on towards success.
Yes, well, I'm hoping it puts everything in context as well, so that the recent study, it's clear where it's come from. So, but I'm going to focus on the role of p53 in response to tumor hypoxia.
We'll be excited to listen to you.
Thank you.
Would you like to tell a little bit about yourself and maybe introduce us to your research?
Okay, I'm from the University of Oxford in the Institute of Radiation Oncology within the University of Oxford. And my research group is focused on tumor hypoxia, which might be unfamiliar. So hypoxia is any condition where you have insufficient levels of oxygen. Wow. And these conditions often happen within solid tumours. So most solid tumours have regions which haven't got as much oxygen as they would like.
Is that how the tumour actually survives inside our body? By being hypoxic, and so they are not available for our immune system? Does that how it works? If it's not right, just cancel the answer.
So I don't know about immunology. So the reason that we're studying tumor hypoxia within a radiation oncology department is because hypoxic cells are very resistant to therapy, and that includes radiotherapy. So, as I'm sure you know, the way radiotherapy works is by inducing DNA damage in the cancer cells and leading to their death. Now, for that to happen, you actually need oxygen. So without oxygen, the radiotherapy doesn't induce that DNA damage.
Oh, that's how they actually are resistant to radiation. Yeah. Very good, okay.
So what we find is that when a patient has radiotherapy, the hypoxic cells within the tumour are spared somewhat. So not only do they go on to survive, but they're the very worst cancer cells in the first place anyway, because these cells, as you alluded to earlier, these cells have learnt to adapt and survive in these harsh conditions. And so they're really, really nasty cancer cells.
Okay.
And unfortunately, these are the ones that are spared during therapy.
So what is your approach to make them more susceptible?
So we take a very basic science approach. So I'm interested in the biological signaling that's going on in these cells, because I think if we understand those pathways, then potentially, if we know what the key components are that the cell is dependent on, we can potentially target those with inhibitors, for example. So if we can take away those things that those cells are relying on.
Are you looking at enzymes, certain enzymes in particular, or?
So I study what's called the DNA damage response. So that's headed by the PI3 kinase. The PI3 kinases ATM and ATR. They're kinases. There are lots of drugs against kinases.
Yes.
So we do a lot of taking a kinase inhibitor and seeing how a hypoxic cell responds to that, and then combining it with radiotherapy to see if we get
So are you looking at new kinase inhibitors, or are you looking at repurposing the kinase inhibitors that are already in the market?
I wouldn't say we're repurposing them. I think a lot of people are using these inhibitors as radiosensitizers. What we're doing and what we're being very careful to check is that these kinase inhibitors give us the effects we want when the cells are in hypoxic conditions.
Okay, so you're measuring inhibition during hypoxic conditions. And do you see a difference between them as against the other kinase reaction that they show?
So what we found is that sometimes there are, for example, the ATR kinase. So if you inhibit the ATR kinase with a small molecule, then you can radiosensitize most cancer cells. But what we found is that if those cancer cells are hypoxic, then it actually works even better.
Oh, okay.
So, you know, in the future, potentially, when we get better at determining which patient has got a hypoxic tumour and which one hasn't, then perhaps we can use that information to dictate which
kinase inhibitor you would be
which
using.
drug you might use in combination with radiotherapy.
Oh, that's exciting. So when you're looking at these measurements of inhibition, what kind of techniques are you using?
We rely on a sort of wide range of cell biology. So we mostly do our experiments in human cancer lines, standard cell biology. And then when appropriate, we obviously translate this and take into preclinical testing in mice.
Oh. So your model is mouse model specifically for hypoxic cells, hypoxic tumors?
So we can grow tumors in mice, which will form hypoxic regions, just like a human tumor.
Just like human tumors? Oh, that's exciting.
Yeah.
Well, that was wonderful to listen to your current research. And how about about the future? What do you plan to do next?
It's always difficult to predict where the research is going to take us. I think I wouldn't have been able to predict the last study we'd done a couple of years ago.
I understand that.
So we're very much going to just keep at it and follow the biology and see where it takes us.
Okay, so we should be expecting something big coming from you in future years.
I hope so.
And I would thank you for coming here and giving us a little bit of insight on your research and the future, and wish you a very best.
Thank you very much.
Thank you.